Hi. In this video, we are going to explore where the LU decomposition comes from. That is the theoretical connections between the LU decomposition and Gaussian elimination, at least the forward steps of Gaussian elimination. A key starting point for this discussion is realization that Gaussian elimination is fundamentally reversible. Every row operation that we're doing in Gaussian elimination has a corresponding inverse operation that will undo that effect. If we have an operation that adds a scalar multiple of one row to another, an operation that subtracts the same scalar multiple from the same target row undoes that effect. If we scale a row by some scalar multiple k, if we scale that same row by the inverse of that scalar, 1 over k, we will undo that result. And if we exchange two rows, we can reverse that exchange by repeating exactly the same exchange, just swapping them back. What this leads to is a very important realization that elementary matrices, the matrices that describe the elementary row operations, must be non-singular. If every row operation has an inverse operation that can undo the effect, we can go from A to A prime with some forward row operation, and from A prime back to A by some reverse operation. Well, there must be elementary matrices that describe each of those processes. A prime is EF, the matrix representing the forward step, multiplied by A. But A must equal AER, the matrix representing the reverse step, times A prime. Putting these together, essentially saying, well, A prime must be EFA, we end up with A equals ER times EF times A, which means this product must be the identity matrix, since we're getting back A. Similarly, A prime equals EFA, substituting in this value of A gives us A prime is EFR I A prime. EF times ER must be the identity matrix. We have two matrices that multiply with one another to give the identity matrix, regardless of the order. This is exactly the definition of the matrix inverse. ER must be the inverse of EF. Right? An inverse exists, so it must be non-singular. That was a discussion of a single row operation and the matrix associated with this. What happens then when we put it all together? We recall that forward elimination can be represented by a product of elementary matrices. That is, if we start with A and go through a series of forward steps, through a series of intermediate matrices until we reach a final upper triangular or echelon form after R such steps. Each of these we can represent as a matrix multiplication. So instead of applying this row operation, we can multiply by the corresponding matrix. We then take the result of this and multiply by the corresponding matrix, and so on. And this gives us a long product of elementary matrices multiplied by A to give us U. We collapse that big product into a single matrix that we call F. F times A equals U, where F is a product of elementary matrices. Now, if we apply the same idea in reverse, we start with U, which is our AFR, the result after R steps of forward elimination. We take a backward step. That takes us to the previous matrix, another backward step and continue this until we reach the step right before A, and our last step takes us back to A. We can also represent these steps by matrix multiplication. U is multiplied by the matrix corresponding to this first operation. And then the result of this is multiplied by the matrix corresponding to the next one, and so on. And we get a perfectly analogous expression. I'll call this matrix R, the collection of all of these elementary matrices multiplied together. R times U gives us back A. Now, we have our forward expression. F operating on A takes us to U. R operating on U takes us back to A, both of which we can express as this product of the forward or reverse elementary matrices. But we have already noted that each of these individual elementary matrices are related by a matrix inverse. The elementary matrices for the forward and reverse steps for any given step are inverses of one another. The order we apply them is opposite, right? If we take steps 1, 2, 3 until R for the forward steps, going backwards we take R, R minus 1, and so on. And so we have a relationship that the ith reverse elementary matrix is the inverse of the R minus ith elementary matrix for the forward steps, and vice versa for the relationship of Fi to the Rith matrix for the reverse process. So if we now take this product of matrices for R, we see that this product of elementary matrices for the reverse process gets replaced by an inverse of the elementary matrices for the forward process. Noting this swap of order, this product counts backwards, starting at R, and then going to R minus 1, R minus 2, all the way down until 1. This product counts forwards from 1, from 1, 2, 3, and so on. Actually, this should I to R, not R minus 1, but I will correct that. Now, because of the rules of matrix algebra and how the matrix inverse propagates into a product, remember that AB inverse equals B inverse A inverse. This product of inverses of matrices can be converted to an inverse of products of matrices where we have to swap the order again. So the order ER R minus I gets changed to EFI inverse because of this relationship. And then we have to swap the order that we do the multiplication again when we remove this inverse out of the individual matrices and instead apply it to the whole product. Right? And I will just make that little correction here. This should actually say from 1 to R instead of from 0 to R minus 1. Right? Now, if we take a look at this, what is this matrix? This product of the forward elementary matrices of R minus I, starting from I equals 0 up to R minus 1. This is our definition of F. R equals F inverse. This isn't too surprising when we actually then sort of think about how all of this sort of fits together. We have, if R equals F inverse, we have RU equals RFA, and we know that that should equal A. It makes sense that this is, of course, F inverse. but we can get at it from multiple perspectives. Okay. So we've now worked out that the inverse of the forward elimination matrix achieves reversing elimination. That is, F times A gives us U. This is forward elimination. A equals F inverse times U. This reverses elimination, taking us back to A. Now the question is, what do F and F inverse look like? What's their structure? Do they have a special structure? Can we compute them easily, or as opposed to multiplying many, many matrices in a string? Okay. To begin this discussion, I want to sort of focus our attention and remember that we're only looking at forward elimination, not back substitution. And if we follow forward elimination strictly, that is sort of the algorithm form of forward elimination, not using tricks to simplify our by hand arithmetic, but just a set of rules that will always work. We never scale rows. Scaling rows is part of back substitution, right? Part of taking us to a reduced row echelon form where the pivot variables are all 1. We do not need to do this during forward elimination. And in many, and in fact in most cases, row exchange is not needed either. Finding a 0 in a particular pivot that we need to do an exchange to correct is a fairly rare thing in the sort of the grand scheme of the space of matrices. Right? What this leads us with is a primary elimination operation, one elimination operation that we repeat over and over again as the primary driver of forward elimination. And this is a elimination step where we take the row K and we subtract a multiple of row I from it, where I is always above this entry. Right? I is our pivot row, and in this case, J is our pivot column. So Aij is the pivot entry we're trying to eliminate, and we subtract a multiple of row I, where the scaling factor is we divide through by Aij and multiply it by Akj, the corresponding element in the row we're trying to eliminate on. This is our primary driver of forward elimination, and occasionally, in some cases, we may need to put a row exchange in place also. So let's focus on the elementary matrices for these two operations only, initially focusing on the first one, which is the most significant one for elimination. So what do elementary forward elimination matrices look like? Let's start with an example. Imagine that we wanted to construct an elimination step like this. Row 3 minus 3, row 1 minus row 3. This would be a elimination operation we would have if we had some matrix that maybe had a 1 in the first position and a 3 in the third position. How would we eliminate this using this pivot? Well, when we, how do we generate our elementary matrix for this? We apply that same operation to the identity matrix, and we subtract 3 times row 1 from row 3. 0 minus 3 gives us a negative 3 here. 0 minus 0 gives us 0, and 1 minus 0 gives us 1. What we see is we have a matrix that basically looks like the identity matrix, but we have one entry here. And if we will note, the entry that we have here is exactly the same coefficient here. Which entry is this? This is entry 3, 1, where we have the 3 coming from this target row, and the 1 coming from the row we're eliminating on. Right? This basic form generalizes. This is what every elimination matrix is going to look like. It's going to look like an identity matrix that has one non-zero off-diagonal element, and that off-diagonal element is the scaling factor for the elimination operation. Right? We can write this formally as follows. The general form of this elimination matrix, it has entries Eij, where these Eijs are 1 if I equals j. This is the diagonal. 0 almost everywhere else, almost all zeros, but in the special case where I equals k, we're in the row that we're eliminating on, and j equals L, we're in the column that we are trying to use as a pivot. Then we use this scaling factor. Right? Now, when we're dealing, this is true for any elimination step of this form. When we're dealing with forward elimination, our pivots are always above our target rows. We're always moving from the top to the bottom. And what that means is that the pivot column, the pivot row L, has to be less than the target row. Right? The pivot row is always above the target row. L will always be less than the K. This means that this entry in the context of forward elimination is always below the diagonal, as we have in the example. Right? So we have an example that kind of gives a feeling for what these look like and a general form that we can generalize to. Now, what happens when we multiply forward elimination matrices? We take multiple steps of forward elimination. Well, each of these is a matrix of roughly the same form, and the result turns out to also be a lower triangular matrix with 1s on the diagonal. This is a general sort of rule that the product of upper triangular matrices must be an upper triangular matrix. The product of lower triangular matrices must be lower triangular. And in both cases, if both matrices only have 1 on the diagonal, the result also will. Right? I think the easiest way to demonstrate this result, which can be proven, is to and it was actually proven in one of the challenge problems on homework 3, I believe, is that we go through an example. So let's consider the example presented here. We have imagine some A transformed to some U. Doesn't really matter what A or U are. We're not actually going to write those down. But imagine that we have a set of 3 steps. If this was a 3x3 system, right, we would typically need 3 steps of forward elimination. We first of all eliminate a second position from using the first row. And sorry, this should be obviously a 2 in this position. And we similarly eliminate row 3 using row 1. This would be the 2 first steps using the pivot in the first position. And then take a second operation where we use the second row as a pivot to eliminate below in row 3. 3 steps. We can write down matrices for each of these. We know what the general form is. The general form for this elimination matrix, subtracting 2 times R1 from R2, is an identity matrix, 0 on the diagonals, where entry 2, 1 is a negative 2. For this one, what's the corresponding entry? It's an identity matrix, all zeros, but with entry 3, 1 as a negative 3. What's the elimination matrix for this? It's an identity matrix, 1's in the diagonal, 0's everywhere else, with a +1 in position 3, 2. Position 3, 2. Right? So we can directly write these elementary matrices just from this rule, from our standard form. What happens when we combine these steps? Remember, how do we apply these to A? We would apply E1 times A, and then E2 times the result, and then E3 times that result. So the product we want to sort of look at is E3 times E2 times E1, E3, E2, E1. And we can work through that multiplication. I'll first of all multiply these two, and we have, well, the first row here is 1, 0, 0. This is going to have the impact of pulling out the first row from the product because we have 1 plus 0 plus 0. Right? And so the first row becomes exactly the same. The second row, 0, 1, 0, is going to have the effect of picking out the second row. 0 plus 1 times this plus 0. 0 times 1 plus times this plus 0. So we end up with negative 2, 1, 0, exactly like this. The third row does something more. We actually have to compute this. Negative 3 plus 0 plus 0, negative 3 in this position, 0 plus 0 plus 0, and 0 plus 0 plus 1. So we get this last row, 3, 0, 1. Then multiplying now by the next matrix gives us, again, this first row, 1, 0, 0, is going to pick out the first row, so it's still 1, 0, 0. This second row is still going to just pick out this second row, negative 1, 2, 0. And this last row, go through the multiplication, 0 minus 2 minus 3 is negative 5, 0 plus 1 plus 0 is 1, and 0 plus 0 plus 1 is 1. So we get a final form, and we see it does have this same feature. It's lower triangular, it has 1's on the diagonal, and it has other entries below. Right? So we see that this forward elimination matrix, combining all of the steps, is also a lower triangular matrix. It turns out that the inverse of this is also lower triangular. You can actually get this directly from thinking about inverses, and it can be proven that the inverse of a lower triangular matrix also has to be a lower triangular matrix. Another way we can demonstrate that, however, is simply by taking the same process and walking through the inverse of these same steps. If a forward elimination process is subtracting a certain multiple of the row, and the step that reverses those is simply adding the same multiple, clearly the underlying elementary matrices have to have the same structure. And we've seen that to invert the forward elimination, we take the same steps, we just apply in the reverse order with this sign change. So applying the same example that we just looked at, but now going backwards, U to A, would be subtracting the second row from the third, and then adding 3 times the first row to the third, and adding 2 times the second row to the second. We can again generate the same sorts of matrices. The backward step 3 will have a negative 1 in the 3, 2 position, as we have right here. So that's 3, 2, negative 1, 3, 2, negative 1. For the second step, 3, 1, plus 3. For the first step, or the backwards, the inverse of the first step from forward elimination, is 2, 1, put a plus 2 there. The 2, 1 position, put a plus 2. Generate these matrices directly from our standard form, and then look at their product. Again, how would we apply these? We would first of all apply the E minus 3, then E minus 2, then E minus 1. So we evaluate the product in this order. I'm not going to walk through the arithmetic, but what you will get when you do this is another lower triangular matrix with 1s on the diagonal. Okay. So what we have here is we've now seen that both the matrix corresponding to the forward steps of elimination and the steps corresponding to the reverse of that process, the inverse of that, right, are lower triangular matrices with 1s on the diagonal if we don't use any row exchanges. Right? This is an important point. How did we get to this point? We only used the standard elimination steps. We didn't look at any row exchanges. Right? Tying this together with what we saw before, we have a forward elimination matrix A equals U, inverse of that matrix A equals F inverse U, and both of these are lower triangular matrices with 1s on the diagonal. What was our target for LU decomposition? It's trying to express A as a product of a lower and upper triangular matrices. We have done that. How do we do that? We simply define this inverse, this F inverse, to be L. It is a lower triangular matrix, 1s on the diagonal. This is what we are going to be defining as L. And once we've made that definition, we can also rewrite this expression, FA equals U, as U equals L inverse times A. LU decomposition. L is the inverse of the forward elimination matrix. L inverse is that forward elimination matrix itself. We have reached an LU decomposition just using the idea of elementary matrices and thinking about their structure. Now, that argument, however, relied on row exchanges not happening. We know that sometimes we do need row exchanges. So how does that affect our analysis? Let's start with thinking about what elementary row exchange matrices look like. Consider an example, exchanging the first and the second row. Well, how do we generate the elementary matrix? We apply that operation to the identity matrix. We swap the first row from the second, and we get something like this. All right? And the general form is always going to be an identity matrix with 2 rows swapped by definition. How can we express that in general terms? Well, we might say we have some E is EIJ, and along the diagonal, most of the entries are 1, with an exception of the 2 rows being swapped. So we don't have 1s at the positions we're being swapped. Most of the other positions are 0s, but there are 2 exceptions. We have a 1 in the position 2, 1, where we've just kind of taken this entry. We've made I equals K and J equals L. And we also have an I in 1, 2. So 2, 1 and 1, 2 both have a 1. That's sort of represented here for an arbitrary swap of rows K and L. This is what row exchanges matrices will always look like. What happens when we take multiple row exchange matrices and we multiply them together? Well, every multiplication corresponds to a row swap, right? Exchanging rows. And how do we generate the first one, these sort of elementary matrices? Well, we start with the identity matrix. So the result of applying multiple row exchanges, the result of multiplying multiple row exchange matrices, is going to be an identity matrix with the rows scrambled. Now, what does such a matrix look like? Well, the identity matrix, just sort of to be clear for the 1 by 1 case, write it down so that we have it here, has exactly 1, 1 in every row. And it has exactly 1, 1 in every column, the identity matrix that actually happens to be in exactly the same position. When we start swapping around rows, well, we still have to keep each row has a single 1 because we're not adding or subtracting any rows, so that structure has to be the same. So we still have to have a 1 in every row. Also, we're not moving around the columns, and so every column also still has to have exactly 1, 1 in it. Right? So this kind of matrix has exactly 1, 1 in every row, exactly 1, 1 in every column, and everywhere else is a 0. Right? We have can see some more examples of this. Let's think about how it happens when we multiply two row exchange matrices together. Imagine that we're taking some A to some A prime by first exchanging rows 1 and 3 and then exchanging rows 2 and 3. Well, the 1, 3 exchange, we put row 1 into row 3 and row 3 into row 1. The 2, 3 exchange matrix, row 1 looks the same, but row 2 and 3 get swapped. When we combine these, we first apply the first one, then the second. So our order is E1 on the right, E2 on the left. And multiplying these through, we end up with a matrix that looks like this. Again, it has 1, 1 in every column, 1, 1 in every row, zeros everywhere else. 1, 1 in every column, 1, 1 in every row, zeros everywhere else. 1, 1 in every column, 1, 1 in every row, zeros everywhere else. This general type of matrix is known as a permutation matrix. It's a special name we give to a matrix that has the effect of scrambling rows if we multiply it by a matrix, putting the permutation matrix on the left. A permutation matrix is simply a matrix that has this property. It corresponds to a product of elementary row exchange matrices. All right. Now, it has a lot of structure to it. It has only a few non-zero entries. All of those non-zero entries are 1, but it is not upper triangular. It is not lower triangular. We can see right here we have some values above the diagonal, some values below. If you think about the rule of needing a 1 in every row and column, you'll figure out that actually the only permutation matrix that is an upper triangular or lower triangular matrix is in fact the identity matrix. There aren't any others. Okay. Now that we have at least a way of expressing row exchanges in a matrix, we get the final piece we need. And this takes a little bit of a logical or intuitive step. If we knew in advance, right, where we would need to exchange rows, it turns out that we could do those before we start. Right? That's not what we do when we're applying Gaussian elimination, what we have been doing in applying Gaussian elimination so far. What we've been doing is we've been starting in the upper left-hand corner, eliminating, moving down and to the right, down and to the right, and if we need a row exchange, we do it and then continue. So row exchanges in our default approach to Gaussian elimination was being done on the fly, interspersed between the elimination matrices. If we do that, then our product of elementary matrices would have permutation matrices mixed in with elimination matrices. We would no longer have a nice, clean structure. But if you think about what is it that causes row exchanges to be needed, it's that there's some dependence between particular rows and the steps moving sort of through Gaussian elimination that is going to create those. Right? We could do it first, right? So maybe let's just throw a brief example of something that would require a row exchange here. Let's say that I had a matrix 1, 1, 1, and then the matrix, let's say 1, 1, 2, and the matrix 1, 2, 1. Normally what we would do for Gaussian elimination is we would start here and we'd eliminate downwards, and we'd get 1, 1, 1, 0, 0, 1, and 0, 1, 0. We need to then do a row exchange, and we'd then get 1, 1, 1, 0, 1, 0, 0, 0, 1. Right? That's what we would have done. What if we swapped these two rows first? We look ahead and we say, I needed to swap these two. So as a first step, I write 1, 1, 1, 1, 2, 1, 1, 1, 2. Swap first, then do elimination, the same procedure, 1, 1, 1, 0, 1, 0, 0, 0, 1. By applying the swap first, we precondition the matrix, we prepare the matrix such that it is directly solvable by only elimination steps. Right? This can always be done conceptually, although how you identify what row exchanges are necessary may need you to actually go through elimination steps to try to sort out which ones you would need. But you can always then conceptually go back and say, let me apply those up front and then move forward with Gaussian elimination. When we do that, we end up with a new framing of the elimination process, where we start with some matrix A, and we only apply necessary row exchanges first to some A prime. These row exchanges can be represented by a permutation matrix. A prime equals P times A. We've now set things up. We've preconditioned the matrix so that A prime is ready for elimination with no row exchanges. Following through those steps to an upper triangular form, this elimination matrix does not require any row exchanges, so it is the L inverse. It's a lower triangular matrix, right? U is generated by L inverse times A prime. A prime, of course, was P times A. This gives us U equals L inverse times PA, or PA equals LU, right? Essentially, this preconditioned PA, right? This is, PA is, of course, equal to A prime. So this is really the same LU generation that we did before. A prime equals LU, but A prime also equals PA. So PA equals LU, where P is the matrix that executes only row exchanges, and L is the inverse of the matrix that executes the elimination steps. It reverses the process of forward elimination. Okay. That wraps up our derivation of the LU decomposition. We see that in this special case where we don't need row exchanges, which actually is quite common, we can purely write a matrix as A equals LU. And in the more general case where we may need row exchanges, we can always precondition our matrix with a permutation matrix and then apply exactly the same approach. Right? P, permutation matrix. L is a lower triangular matrix with ones on the diagonal that represents the process of Gaussian elimination, actually taken backwards. And U is the echelon form that we get after Gaussian elimination on our starting matrix A. Okay. With this derivation, we're now set to start exploring how we use the LU decomposition to solve linear systems effectively, especially when we have multiple right-hand sides. How we use those results not only to get unique solutions, but also to get general solutions when we have many, and to identify right-hand sides that don't have a solution. Those are all of the ideas that we are going to address in the next video. Thank you, and goodbye.